We have seen simple sequences like the following: 1, 2, 4, 8, 16. For this simple sequence, you know the pattern is every time that the next term will be twice of the current term. So 2 equals 1 times 2, 4 equals 2 times 2, 8 equals 4 times 2, 16 equals 8 times 2. And in general, you know the term look like 2 to the power k. This is example 1. So this is a sequence that we know. It's a very easy sequence. A second sequence, I also can know, is, let's start with, say, that's a 2. The next is a 6. Next is 18. Next is 54. And next is 162, and so on. So what's the pattern of this sequence? If you take the ratio of the next term over the current term, you see the pattern is that ratio is a constant. So 2 times 6 equals, 6 divided by 2 is a 3, so 2 times 3 equals 6. 6 times 3 equals 18. 18 times 3 is 64. 64 times 3 is 162, and so on. And for this sequence, the general term look like 2 times 3 to the power k minus 1. Actually, to be exact, the first sequence that if k is the index of the term form is 2k minus 1. Because when k equals 1, the value is 2 to the power 0 equals 1. Okay, so such a sequence is very easy. And the general pattern of such sequences is the ratio of the next term over the current term is a constant. Okay, so that's a pattern of a lot of sequences. And we give a name to such sequences. We call it a geometric sequence. So that is the definition of a geometric sequence. A geometric sequence is the ratio over the next term over the current term is always a constant for such a sequence, and such sequence is called a geometric sequence. Why it's called a geometric sequence? One reason is the following. It has a geometric meaning. Let's see. So given a segment length of A, what is the length? Okay, I just said the definition is the length of that segment is length A. So the length is A. Given that A, if I draw a square, what is the area of that square? The square is, the area is A squared. Okay, the length here is A. But for, if I using the segment of A and draw a square, the area of that thing is A squared. Now, what if I draw A using a cube? Using length A. So this is A, and A. What is the volume of this cube? It's A times A times A to the cube. And now in 4 dimension, I really cannot draw this anymore, but people call it a hypercube, and the volume of that hypercube is A to the 4th. Now it's going to look like something like this. We try to draw it, but you cannot see it in our three-dimensional world. So it's going to be like something, another dimension, and you have something coming out. Okay, don't treat it very seriously. But it basically has one three-dimensional cube, and then you kind of shift by A and in a different axis. And the volume of that thing, a hypercube, is a to the fourth. So you see that for this kind of a volume in different dimensions, you see the ratio of the next term over the current term is A, and exactly follows such a sequence. And this has a geometric meaning, and maybe because of that reason, we call it a geometric sequence. In this lecture, we're going to talk about how we sum over such a sequence. And we're going to focus on this two special examples, how we're going to sum them up. So let's look at the following. For our first example, we want to sum up the sequence of 1, 2, 4, 8, 16, and so on. Let's say we want to sum up all the way to 2 to the power 10th. Okay? So we want the following. S equals 1 plus 2 plus 4 plus 8 plus all the way to 2 to the power 10. And remember, 2 to the power 10 is the 11th term. How are we going to sum this up? One way is, of course, just brute forcefully doing it. And actually, this is not a bad way if you observe the pattern. Let's see. We just sum up. Let's do the first sum. So the first sum, if we sum 1 plus 2, is equals 3. And how about the sum of the first three terms? 1 plus 2 plus 4 equals 7. 1 plus 2 plus 4 plus 8, that equals 15. So if you write that down, it's 3, 7, 15. And what is the next term? 1 plus 2 plus 4 plus 8 plus 15 equals 31. Do you see a pattern of this sum? It's actually, if you are careful, you see the sum of the first two terms is just the next term minus 1. Sum of the first three terms is the next term minus 1. Sum of the four terms is the next term 16 minus 1. So you see this is 3 is the next term is 4, 4 minus 1. 7 is the next term, 8 minus 1. 15 is the next term, 16 minus 1. 31 is 32 minus 1. So it's always the next term minus 1. So you can guess 1 plus 2 plus all the way to the 2 to the 10 going to equals what? It's going to be the next term, which is 2 to the 11 minus 1. Okay? And that's perfectly fine. But also we're going to talk about another technique which is more general and extendable to all those geometric sequence sum. And that technique goes like the following. So, okay, this brute force and observing the pattern is first method, which is, in my view, is also very, very powerful. Okay, I like this method. The second method is more general and extendable. So I'm going to call this sum is going to be equals 1 plus 2 plus 4 plus all the way to 2 to the 10 equals an S. Now one thing we observe is the next term is always the current term multiplied by 2, right? That's the pattern that we know from the beginning. So let's do the following. Let's do 2 times S. So essentially, I want to multiply each term by the constant 2. Okay, so this becomes 2, this becomes 4, this becomes 8, every term minus multiplied by 2. This 2 to the 10, which is the second last term, and plus the last term is 2 to the 11, because every term I multiply by 2. So why I'm doing that? The reason I'm doing it is once the term is multiplied by 2, the current term becomes really the next term. So this 2 is the same as this 2. Of course, the first one now does not appear in this current term. And in this current term, the last term, 2 to the power 10 times 2, 2 to the 11th, also does not exist in S. Now the next step is taking a difference between the 2S and the S. So in these two equations, I'm going to take the second equation minus first equation. So the right minus right, left minus left. So 2S minus S going to equal 2 plus 4 plus 2 to the 11, which is the right side of the second equation, minus 1 plus 2 plus all the way 2 to the 10th. Okay, let's move on to the next page. So let's go back a little bit. We write down S equals 1 plus 2 plus 4 plus all the way 2 to the power 10. And now we multiply both sides by 2. 2S equals, this becomes 2 plus 4, every term I multiply 2, plus 8, plus all the way 2 to the power 10, which is the 2 to the 9 term, times 2, and plus this term becomes 2 to the 11th. And the next step is a key step. I'm taking a difference between these two equations. Left side, 2s minus s equals s. So if I call this equation 2, this is equation 1, I'm doing second equation minus the first equation. Okay, what I get is the left side is 2s minus s equals s. The right side equals, I'm going to just write down 2 plus 4 plus 8. Here's nothing but I'm taking all the right term of the second equation minus the right term of the first equation. But here you see a lot of things are common. And that's exactly because I'm taking multiply 2, which is the ratio between the next term and the first term. So by multiplying 2, I'm transfer the current term to the next term. So I cancel a lot of common things. The 2 appears there, 4 appears there, except that the last term, there's no last term, and the first term of the right side of the first equation, the 1, it does not exist, right? So everything cancels except one term in the second equation and one term in the first equation. That's equal to 2 to the 11 minus 1. And that's the answer. S equals 2 to the 11 minus 1. And this is the second method of calculating the sum.